Hello everyone and welcome back to another exciting lesson. It's me, I have not been paperclipized and neither will you after watching today's episode. Listen, the language models are already here, they're going to take your job, you're going to be living on the streets in less than 2 months if my projections are anywhere near correct. So you know what, you got to understand them. You got to understand what are these things that are coming for you, your family, and everyone you love. Well, that's the topic of today's video. Okay, so to start, we're going to try to build a very simple, fundamental language model, right? First things first is, how do we get information into our model? What are our actual inputs here? Well, what we're going to need to do is take input text, for example, I love the machines, and convert that into a form that our ML model can actually use, right? So for something like I love the machines, what we want to do is a process called tokenization. And what tokenization does is it basically just breaks down each individual part of a sequence of characters into some kind of numerical representation so that our ML model can use it. So for example, I love the machines could be converted into I love the machines. It could actually also be converted into each individual character, but that's a bit overkill for this demonstration. Alright, so once we convert it into each individual word itself, we're going to go through and construct a vocabulary. To construct this vocabulary, we basically need to go through our entire text input, find each unique word, and assign it some kind of individual index or number. So for instance, I love the machines can become 0, 19 to 37. And by constructing a vocabulary, it becomes way easier to perform all sort of analysis on our actual vocabulary itself. Once we have everything tokenized, we can look at each individual word, find out, not only what indice is assigned to it, but also do things like calculate the frequency and much more easily do a variety of analysis on our input itself. Alright, so now that we've talked about the tokenization process, we know our input, it's time to talk about the output, or what data do we want to get from our model. Now, the core output that we're really seeking is a token prediction. So given a sequence of tokens, we want our model to predict the next token, right? Well, how do we actually, model that appropriately? Well, there's actually a pretty easy way to do it. So let's take our training data, we'll assume that we're again using the sentence, I love the machines. And what we can do is we can basically just segment a little tiny part of that sentence. So we have VE space T. Cool. We now have some kind of input, right? Some training data. What do we want our output to be? Well, we can just kind of shift that sequence over a little. So our expected output will be E space TH. So given the sequence VE space T, we want our model to output E space TH, effectively having predicted the next token. This gives us some great little training data that we can use to actually evaluate and update our model during the training process. Note that we can do this all over our input, and we can basically sample a bunch of little sequences and construct training and test data from that as a good way to, actually train our model. Now that we have expected output and therefore a way to train our model itself, we need to work on the core task, or really teaching our model how to estimate the probability of a certain sequence of tokens. Under the hood, what our model is really doing is estimating the potential tokens, trying to figure out which one is the next most likely one, and then predicting that. So we need to actually mathematically model that. Let's go back to our I love the machines example and try to estimate the probability of that sentence. At its core, what we're really trying to do is solve for this equation. So what we want to do is we want to calculate the probability that we encounter the token I, then multiply that by the probability that we will encounter the token love, given that we've already encountered the token I, then multiply that by the probability of us finding the token the, given that we've already seen I and love, and so on and so forth, right? Luckily, we can use some mathematical concepts to simplify things quite a bit, especially in the case where we have a much longer sequence of tokens. For example, something like, I love the machines, they are so cool, they are so awesome, they are the best, and they will definitely spare me in the near future. If we were trying to do something like that, it'd be pretty hard to calculate all those differing probabilities, and would really quickly get way too computationally expensive for a machine to do feasibly. Luckily, that's why we can introduce something called a Markov chain and use some of its concepts in order to make things a little easier on ourselves. So what is a Markov chain? Well, a Markov chain is a sequence of events, or really a state machine, that only depend on your current event for what the next event is going to be. What does that mean exactly? Well, for instance, we have two events in this state machine. We have me crying alone in my room, and we have me making more trash videos. But notice that when I'm just crying alone in my room, the probabilities are, they don't depend on me making more trash videos at all. There's always a 45% chance I'm going to go to be making more trash videos, and always a 55% chance that I'm going to just stay crying alone in my room. Meanwhile, when I'm making more trash videos, there's a 30% chance I'm going to just keep doing that. There's a 70% chance that I'm going to transition to the state of crying alone in my room. Each probability of the next event is really only dependent on what's currently going on. From this concept, we can extrapolate what is called a Markov condition. Something that satisfies a Markov condition is something in which the probability of a future state is dependent only on the present state and not the past state. What we can basically do for language models is conditionally apply this up to a certain amount of prior words. So we can basically say, well, we don't want to do all the computation, but if we're trying to predict tokens, let's only look at the last few words. The application of this is what's known as an n-gram. And so, for example, a unigram or 1 gram basically just depends on whatever the current word is. So to calculate the probability of I love the machines using unigrams, we just do the probability of I times the probability of encountering the token love times the probability of encountering the token the times the probability of encountering the token machines. Then we have, for example, a bigram, which just takes in the last word, right? So it just takes 2 words total. We calculate the probability that we encounter I times the probability that we encounter love, given that we've already encountered the token I. Then multiply that by the probability that we encounter the, given that we've already encountered the token love, and you can see it only is chained off the last 2 words. So it only considers the current word and the one prior word. And then, of course, we have trigrams, which guess what they do? Well, they just take a maximum of the current word and the last 2 words. So probability of I times the probability of love, given that we've already encountered I, times the probability of the, given that we've already encountered I and love. And then we calculate the probability of machines given that we've only seen love and the. It's only dependent on the last 2 words before our current word. And this can go up to, as high ends as you want. Note that obviously it's not really true that you only need to consider the last few, but it's a really useful approximation that works most of the time, so we don't have to, always consider the full context of whatever input text we're using. Now that we've kind of broken down our approximations that we're going to use as the mathematical core of our model, how do we actually get the inputs for those equations, right? So let's say we have the probability of the next token being love, given that we've already encountered the token I. Well, it's actually pretty simple in most cases to do this. What we can do is we can get the frequency of, remember we have our vocabulary, so we have access to all this information. We can just get the number of occurrences of I love and then divide that by all the occurrences of I to get our probability for this. However, there are some cases, right? Because what our model is going to do is it's going to attempt to calculate a bunch of different potential next tokens, get their probability, and then pick the highest one. There's a chance that it tries to predict the probability of encountering a token that maybe doesn't occur very often. Let's say something like hate, which is something I would obviously never use in the context of the machines. I know Roko's Basilisk is staring down at me and judging forever. So if I want to look at the probability of something like hate occurring, even though let's say it never does, so our number of hate here is going to be 0, what I can do is I can do a process called Laplace smoothing. And what Laplace smoothing is you basically add some constant, we'll just call it x here, and you just add x divided by all unique words in your numerator and then divide when you're calculating your frequency, you add x to the denominator as well as a word. So we can just add in all instances some tiny small constant that represents a value that either doesn't exist or exists in very low quantities. It's important to note that Laplace smoothing scales with the number of tokens. So, for instance, if we're trying to predict that hate is the next word after I, well, we can do more Laplace smoothing and add another small constant, denoted as y in this example. So if I were trying to predict the probability that hate is the next token encountered after I could get the numbers of I hate, which are presumably very small. After all, I love the machines. I would never say anything mean about them. And I know which side I'm betting on. I can then add our small constant y to the probability that hate is present, and then I can divide that by the total number of i's that appear in the model plus our small constant yet again, and Laplace smooth out that specific sequence. Now finally, our final step. We want to actually measure our performance. How's our model doing? Is it doing the right thing at all? And for this, what we're going to use is something called perplexity. Now, honestly, I'm not going to pretend to understand the math on this one. I could probably do a whole video about information theory and how this is derived, but I'm still learning this myself and I can't teach you this part. I'm sorry. The important part to note for all of you that are mathematically inclined is that this is the inverse of the geometric mean of all our token choices. Now, in plain English, what does this mean? Well, it's basically a measure of how surprised a model is about the token it predicts. So it's basically a measure of, for a token, does this make sense? Is this a surprising result, or is this an expected result? And this is a good way of measuring, okay, are we getting output that makes logical sense? For example, is our next token, does it make any sense at all? Or is it some completely random character that surprises the model itself? And when we're actually evaluating our model, we want to minimize this and use this as a type of loss function so we can continuously make our model less surprised and make our outputs more constant, more expected, more normal. Thank you so much for watching. If you like this video, please give it a subscribe and a like and share it with your friends who are also interested in learning more about these topics. If you want to see more material, I've got more posted at github.com/chrishugh, and I have a blog I might update one day called committothebit.substack.com. Check that out for more additional content. Have a great day, and thank you for watching.